Really appreciate it. As you can see here, we've got our Professor Robert Cross here from Warwick University, and he's going to be talking to you about integrated health as a pathway, or integrated science rather, and having a look at that, what that means, what that means in terms of future careers, what that means in terms of what you would study, etc. So as always with these things, if you've been to them before, you'll know that if you want to ask a question, you simply add that to the chat function, and then I'll put it to Professor Cross at the end of his talk. Otherwise, just listen for the time being and have a think. And while you're listening, just think if there's any questions you want to answer. If you don't want to put them in the chat, you can email them directly to Miss Shazza or myself or Miss McAteer as well. Okay, if you don't want to put them on the public chat forum. Okay, but we're going to hand over to Professor Cross now. Professor Cross, would you like to tell us a bit more about integrated science at Warwick?
Well, that's exactly what I'm going to try and do. Good morning, or in fact, good evening, everyone. I'm going to just try and explain, what this course is all about. It's a very unusual course, as you'll see, and so I need to sort of go through this in a little bit of detail so that you can really understand what this course does, what it's aiming to do, and how far it's succeeding in doing that. So I'm going to, I may revert to this view, but I'm going to try going full screen. Here we go. Now, hopefully that's okay. So yeah, so the point of this course really is to train you as scientists. And everything that we're going to teach you on this course is really to do with the techniques that you can marshal in order to address this question: how does life work? And I'm going to try and just explain what I mean by that now. So today we're going to step through this sequence. I am going to give you a little brief taster about halfway through of what it would actually be like to be in the teaching experience on the course. And then we're going to sort of sandwich that with views of what we've been up to this year, sort of reports from the coalface, as it were, and also some interviews with some students to sort of show you how they've been getting on. So the course is new. We've only just begun 1 year ago. It's a 4-year course. It's an integrated master's course, and it's the only thing of its kind in the UK. A 4-year undergraduate master's course. That means that there's a master's degree included in the undergraduate course. And the quote bubbles here are just sort of things that some of the students have said to us when asked to report on their experience this year. The whole point really is to develop you as scientists, as I mentioned earlier, in pursuit of this question about how living things work. So what exactly is integrated science? So the central idea is to be able to take the ways of thinking and the techniques which belong in these different scientific disciplines and actually combine them as appropriate in order to address this question: how does life work? How do living things work? How do the mechanisms inside living things work? And to do this, clearly, we need to change the way that we teach you, because the conventional courses, single discipline courses, are sort of well established, but this is really new territory to try to leave the door open to learning techniques from different disciplines in pursuit of scientific questions. Here's a sort of a list of the features of the course that we've set up. So that, as I said, this is a 4-year integrated master's course, and the central practical principle that we're working to is to actually learn science by doing it. So we put you in the lab straight away. As soon as you arrive on the course, you'll be standing in the lab, and we will take you through, very closely supervised, lots of support. We'll take you through everything you need to know in order to get going doing research in the lab. And then the teaching is a bit different as well. So the teaching on this course is actually from researchers. So everybody, more or less everybody in the course is coming from a background of postgraduate teaching rather than undergraduate teaching. That means, we're used to doing research and telling each other about research. And now we're really extending ourselves, as it were, to sort of younger recruits. And the spirit of the course is really drawn from the enthusiasm of the instructors for the scientific things that interest them. So I'm a course director, and what I've told people is, try and teach from the things that you're actually interested in. And that way, students are going to benefit from your enthusiasm for what you do. So we're trying to keep that as a principle as well. I mentioned that you'll be in the lab straight away. Well, you're also going to be getting classes, and there's roughly equal time in the first year of the course. You spend roughly equal amounts of time doing experiments in the lab and sitting in class, really learning the background information that you need to know in order to follow what you're doing in the lab and understand what scientific questions you're asking in the lab and the principles that underlie those questions. And also learning in the classroom the analytical techniques and the concepts that you need in order to interpret your experimental work. Another principle is that we are emphasizing computing. So this is, for anybody who does research, this is sort of obvious. Computing is simply getting more and more important as a key tool for science. And we have adopted that as a principle. You don't need to know any computing when you join the course. We'll assume that you've never done any coding before, and we'll take you through it. But that emphasis on computing as an increasingly important tool is central. Another principle is very few people are actually on this course. At the moment, we have our pioneering cohort of students. As I say, we've only been running for 1 year, and we started out at sort of half strength deliberately to make sure that we kind of iron out any wrinkles in the fabric of the course. And then we're aiming to rise to a maximum of 25 students over time. And that's because of the experience that we need to deliver, necessitating personal attention. So, you need face time with active researchers in order to develop optimally. And that means we need to limit the numbers of people on the course. So it's a challenging course. Everybody accepts that. That's challenging for the students, and it's challenging for the instructors because of its recipe. But it's also great fun and really rewarding. And as you'll see later on in this talk, students are really positive about the course. Everybody involved with it is very positive about the course. Another feature is that we encourage you to work together. So in the lab, you'll be in a team of 2 to do experiments. And then in the classes, you'll really be in a team that constitutes everybody in the room. The idea is that students are arriving onto this course with slightly different backgrounds from different directions. And if you know the thing that we're working on better than your friend, your neighbor in the classroom, then you're encouraged to help them. So we try to leave behind this whole thing about, we don't speak to each other, when we're in the exams and this kind of thing. We don't operate like that. We operate in a way that we're all on a journey to get better as scientists, and we try and help each other. Students try and help each other. Students try and help instructors, and instructors, of course, are trying to help students grow as scientists. And then, as I mentioned, the final year is just almost, your master's year is just almost entirely focused on experiments. You'll actually do your own self-design project, and we'll help you design that. This is Warwick. This is actually the front page of the Warwick University website. You can just go and have a look around. Warwick is pretty well dead center in England. equidistant from every coast. Warwick is probably, with all due modesty, it's probably the best modern university in the country. Just recently, it's being ranked, exceptionally highly for teaching. So we're actually, oh, there we are in the middle of the country. And if you look down in the bottom right on this, sorry, that's annoying. Okay, down in the bottom right on this slide, you can see that this year we've just been recognized as having the best teaching in the country. So one way we try to explain to people about the course is open days, and it's a regret that you're far away and you can't necessarily attend these in-person open days. So I thought I'd show you some pictures. These are 3 of our current students. This is Harriet and Maddie and Laura, and they're helping out with an open day that we had last month. This is pictures of open days. The October open day involves actually people walking around, and then we demonstrate to them some of the things that you'd be doing on the course. What you can see here on the left is the microscope that you'll be using on the course, and I'll explain a bit more about that in a moment. In the middle is a spot of 3D printing, and on the right there you have Masanori Mishima. My colleague is explaining about Turing patterns, which is a sort of mathematical principle underlying patterning in embryos. And this is more from another open day. This is a recent open day. You get the idea. So, if there are things that you think you would have asked had you attended an open day, then please put them in the chat, and we'll see if we can attend to those. This is George and Laura in the lab. Obviously, this year's been a bit of a strange year. We've had to wear full body armor in the lab, but we've got through it. Oh yeah, the red thing on the bench there is the microscope. I'll explain to you more about that in a moment. Here is a fly embryo. Here's the same fly embryo at different magnification. And what we're doing in these classes is actually watching the process of insect development and measuring the movement of cells within the developing insect embryo. This is a kind of overview of the lab. You can see we've got some nice space. You can just about recognize that students are working in teams with 2. This is England in October, so it's already getting dark at 4 o'clock in the afternoon. But nonetheless, the activity in the lab is kind of cheerful. So I'm going to try now, in the next few minutes, I'm going to try and sort of explain a little bit more about the experience of studying integrated science. What is it actually like to study integrated science? This is the structure of the first year. So I mentioned to you that you're going to spend about equal time in the lab and in the classroom. And then also, during the first year, you will be instructed by a series of different people about different kinds of question. But all the questions that you'll be addressing by experiment in the lab, they're all subsets of this broad question about how does life work. But what we've done is actually develop a structure whereby every 2 weeks through the first year we have a different question. Each of these different questions is led by a particular individual, a particular research scientist. So you get a different instructor every 2 weeks, essentially. And during those 2 weeks, that person is really pivotal for you. I mean, there are other people around in the lab and in the classroom, but that leader of those 2 weeks, is the pivot person. And what we do is these questions gradually develop as we go through the year to subsume longer length scales. But what I mean by that is that we start out with questions that operate at really the atomic and molecular level. And then as we step into the second term, you're already asking questions more about the structure of cells, so organelles and cells. And in the third term, we're up to the level of organisms and populations, and indeed populations of organisms. So that's the kind of the principle on which we've structured everything. We essentially we leave the door open to you using techniques and principles from different disciplines, but those are then marshaled to address questions which just gradually increase in the size, physical size of the question that you're asking. So the length scale increases as we go through the year. And then this will be a typical week in the first year, just to kind of focus you on how your time might be spent. So you can see that on weekdays, typically we're spending the morning in the classroom doing a mixture of lectures and problem sets, and then in the afternoon in the lab. Wednesdays is actually there's a kind of voluntary session on Wednesday morning, which is a sort of computer clinic session. And then Wednesday afternoons is kind of playtime, just going to do some sport or something. And the problem sets and the lectures typically get shuffled together. So the idea of the problem sets is that you sit and solve problems that relate to the material that you've learned in the lectures. And then we typically intercalate those into the instructional material, so we don't have a huge long chunk of lecture. You just generally have 10 or 15 minutes of instruction, followed by doing little problems. And those problems are addressed collectively. As I said, they're not even assessed. We're just trying to use those as tools to kind of test your understanding and improve your understanding. And as I said, the afternoons are in the labs. And here's a bit more detail on that. This is, I don't know how useful this is, but this is actually from my block 3 in year 1. And I'll tell you a bit more about the detail of this in a moment. The thing to notice is that, we've got this voluntary computer clinic thing on Wednesday mornings to try and solve any coding issues that you've run up against. And then the other thing is that at the end of each 2-week block, you write up your experiments. And we do that in the format of a scientific paper. We obviously help you at the outset anyway. We're going to really help you a lot in order to make it possible for you to write a little scientific paper. So we provide a kind of scaffolded write-up to begin with. And then as the year wears on, we kind of drop away the scaffolding and we finish up being able to write your own papers at the end of the first year. And there's some time assigned in those blue boxes to the writing up process, so that we can coach that during the week. So there's a lot of contact time on this course. You are face-to-face with active researchers pretty much the whole time. And then this is a map of the whole course. I mean, you probably don't want to look at this in huge detail. I'd urge you to go to our website and have a look around if you'd like some more detail. But it gives me an opportunity to just explain the rest of the course other than the first year. So the first year actually is probably the most radical aspect of the course, and it only counts for 15% of the total marks for the course. Second and third years, what we're doing is drilling down deeper into the principles of how life works. And to do that, we're using well-established, or largely we're using well-established components that actually come from the School of Life Sciences here. And you can get an idea of the spread of what you can learn. There are some core topics which are on the left there in those brown boxes, and then some options which are on the right. And then at the end of the sequence in the 4th year, like I said, the major component is this extended research project, which will help you design. You're essentially encouraged to find your own scientific question in which you are super interested, and then we'll help you try and answer it. The last thing to mention here on this map is that on the right there, we've got there's a thread of cohort events in integrated science. That means there's student-led activities. So we actually have a society of integrated science students and they can invite external speakers. And so we have, every 2 weeks or so, we have an evening event with kind of pizza and beer and an invited speaker or something. And that's all organized by you, the students. I'm going to go through these slides quickly. These are the people who are actually teaching the course. We hope that they're inspirational role models. They're all running labs here at Warwick successfully. They're all internationally renowned, and they can teach you basically how to be a good researcher because they are good researchers. That's the principle. And then we've had some advice also from postgraduate students in developing the course. In the blue bubble there, I've tried to make the point that everybody involved in this is super enthusiastic about it. And you know, I certainly wish I could have done this course when I was a student. And I think that's true of all instructors and also all the students. So a little bit more detail. I mentioned computing is kind of a central principle. So we give you a computer, we give you a MacBook. And this is a little movie just walking around the class watching people. This is in my block. So this is week 5 of the first year course. You can see that what we're doing is a bit of molecular graphics work here on the MacBooks. So you get to keep these computers for the whole course, and that's a huge advantage for us because we can then coach. We can then coach you, efficiently because everybody's got the same setup. The other thing, here are some bits of coding. This is a bit of non-planning. And the other thing we've done for the course is we felt it's extremely important that you should be able to use high quality microscopy. And the problem is that the high quality microscopes are seriously expensive, so like several £100,000, several $100,000 US, whatever. And so what we've done is developed a microscope for the course, which is sufficiently cheap that we can afford it and actually still delivers extremely high quality imaging. This has the double advantage that we can play around with the engineering of the microscope as part of your education. This is the microscope. It's just sort of animation that shows you how it works. We call it the EduWASM, Educational Warwick Open Source Microscope. And I'm just going to show you some of this in action. Now, this little movie of the light engine. That little aluminium box that's being held in the left hand there is putting out 4-color light.
Looks like on your center.
And there are some images from the year 1 classes now. So this is my friend Andrew McCanch teaching you about cell division. This is chromosome segregation in a cancer cell. Here's one of our students. This is Harriet. That's a terrible picture, sorry about that. This is just to illustrate that despite needing to distance and wear masks and everything, we did actually manage to get some audience participation in the classes this year. And here's an image just emphasizing that we're balancing time in the lab with time in the classroom. And then here's some more footage from the year 1 labs. This is actually from the very first week when you arrive, and just to kind of break the ice, we get you into the lab and we just play. Essentially, we induct you into safe procedures in the lab, and then for this exercise, we got everybody to build a bridge out of spaghetti and then see how much weight it would take. So there's a bridge on the left there. And then on the right here is kind of destruction testing the bridge. So we get you, this one actually took 4.5 kilos before it popped. There we go. You get the idea. So more images from the lab. This is that Drosophila embryo that I was telling you about. You can see a little bit more detail in this sequence. But each of the bright orange dots there, which will come into focus in a minute. There we are. Each of those bright orange dots is a cell moving around inside a developing, living insect embryo. these are those same embryos imaged by a different contrast method on the same microscope. This is a different experiment where we're actually looking at the polymerization of a protein, and those are the polymers floating around in watery solution, being imaged individually. This is a different experiment where we're looking at diffusion. I'll tell you a bit more about this in a moment. And here's a sequence where we're learning not so much about biology, but about physics. And this is a module that's just called light in the first year. So, tight for time, I'm just going to gallop through this taster lecture. This is about water. The reason I wanted to do this is because I want to give you a flavor of what it means to learn something without worrying about whether you're learning physics or chemistry or biology or computing or maths or whatever, but instead just focusing on the question that I'm interested in. So let's skip these. So please focus on this picture. This is a bacterial cell. This is an E. coli, a diagrammed bacterial cell. This is an E. coli cell, which such might be found in your gut. And the questions you might want to ask now about the inside of this E. coli cell might look like, how many water molecules are there actually inside this E. coli cell? If I have one molecule rattling around inside this E. coli cell, what's the concentration of that molecule? And actually, even more, what is it actually like inside the E. coli cell? So this is a simulation, in fact, of what life in the cytoplasm inside an E. coli cell would be like. And I don't know if you've thought about what the cytoplasm is like inside your cells, inside bacterial cells or whatever. But this is a very crowded place. This is a very crowded place indeed. Though each of those colored blobs is a large macromolecule, and you can see that the space between them inside these cells isn't very large. There's a lot of jostling going on as these molecules jump around. There's a thermal motion. And here's another, conceptual aspect of thinking about the inside of those cells. So here's a single water molecule. And just ask yourself for a moment, what do I actually know about water molecules? Maybe you've seen these sorts of pictures, in chemistry about the bond structure of water. But did you know, for example, that those bonds actually move in this fashion? And have you thought about the distances inside a water molecule? So you've probably seen these diagrams, the idea, the kind of Rutherford model of the atom, where the nucleus is a sort of collection of particles jammed together, and then it's orbited by electrons. We've moved on from that to this more orbital based view of atoms. But what about actually the distances? So did you know, for example, how big the nucleus is in relation to the orbitals which surround it? So here we're even going smaller than a water molecule. This is just a single hydrogen atom. And I just want you to just spend a moment thinking about the size of the nucleus relative to the distance of the electrons, the most probable distance of the electrons from the nucleus in that atom. So just take a moment. This is not a quiz or anything. Just take a moment to say, have you actually thought about, how far it is from the periphery of the nucleus actually out to the first electron orbital, the most probable position for the first electron? And the answer is staggering. Right? So the so-called the Bohr radius of hydrogen, which is the distance, the radius of that first electron orbital out from the middle, is almost 5 orders of magnitude greater than the diameter of the proton. So the radius of the proton is in the order of about 10 to the minus 15 meters. And the Bohr radius, the distance out to the most probable position of the first electron, is roughly 10 to the minus 10 meters. So that's 5 orders of magnitude. So if you imagine, if you imagine the nucleus is about the size of a basketball, then the first electron is going to be about 3 kilometers away. I still find that staggering, and it's an illustration of the way we get trapped in ways of thinking. So thinking about that problem just in a very simple-minded way, you learn something that probably hasn't entered your head because of the chemistry way of thinking about things, and probably hasn't entered your head because of the biology way of thinking about things, but is an important point nonetheless. And these are just some simulations that we're running of the rattling of molecules around in a box. This is the 3D diffusion of molecules, and this is a simulation that we had going during my block. And I'm hoping you'll get this going on your, you would have got this going on your MacBooks. And here's a class of the same thing. This is actually visualizing in the lab. We're visualizing the diffusion of a molecule-sized particle and then measuring it. So here's a slightly lighter weight picture. This is the current class of students. At the end of their first year lectures, we asked them to sort of represent in costume their experience during the first year, and this is what they came up with. And now, I'm going to just try and speed up a bit and talk about why you might want to do this. And actually, I'm going to skip this. This is the main message I want to get over. So if you think you might be interested in this, you can ask yourself, what kind of person would be suited to this course, and where is this course going to take me in the longer term? And I want to say that the kind of person that will be suited to this course is the kind of person who's curious about the world. And it's really that simple. These are 3 Nobel Prize winners. And if you look in the speech bubbles, they're basically all saying that the most important thing is your interest in the problem that you are framing. So I would say if you're a person who's curious, scientifically curious about the world, then you should actually think twice about whether this course is the course for you. Venki Ramakrishnan, who is on this picture, actually visited us a few weeks ago, 3 weeks ago, and gave a nice talk. Here he is with the current cohort of students. So he gave us a nice inspirational talk about how to be a scientist. Venki's till recently he was ex-president. He was president of the Royal Society, and he's got a Nobel Prize in chemistry. And he came to talk to our integrated science students about how to be a scientist. This is his book. And what kind of career is this going to set you up for? Well, it's going to set you up for science, and that's the central message here. Science is a career in itself. I do science, I do exploratory science as a career, but it has to be said that is quite a minority activity in the world. There are not many people who actually do research as a career. Basic research, asking questions about how the world works. So the important point to make is that this is really training you to solve problems, and employers are looking for problem solvers. Warwick is actually the top destination for graduate recruiters in the UK, and what those recruiters are looking for is people who can solve problems. And that's true of every possible occupation that you can think of, practically, from politics through to medicine, through to teaching, through to business, entrepreneurship, computing. You're just solving problems, and having the skills to do that effectively and well is what this course sets you up to do. So it's an extremely general training, but it's extremely useful in specific areas, and it will qualify you to do these various different things. I would suggest, and we can't of course back that up with evidence at the moment because nobody's yet graduated from this course, but you see the point. And I'm going to finish off with just with one of these student interviews. This is Bronte, who's one of our first year students who just finished the first year, and this is her impressions of the course.
I'm Bronte Kelly, I'm from Manchester and I'm studying integrated science. I chose integrated science because of the interdisciplinary nature of the course. Because I don't know what I want to do in the future, it allows me to try a bit of everything, but of all seven subjects before committing to a certain field. I've always been interested in science from a young age. I've known that I wanted to do something to do with medicine. I have a lot of people close to me that have suffered with diseases and I've always wanted to find a cure for that in the future. That's always been a dream. I really enjoy the course at Warwick and the small cohort makes it a family style. Everyone's really close and there's always help around. Because the course is new, the professors are always looking for your feedback and always open to suggestions. It's definitely had its challenges, but all the professors have made it as easy as possible. We've been able to do a lot of in-person teaching where possible. Obviously, where it wasn't possible, they made it as good as could be online. I had never studied biology. Obviously, this is quite a biological degree, but I found as I settled in and got to know everyone, there was always someone to offer help. Everyone has their weaknesses. You just work together to get through it. I want to go into a PhD or a postdoc, but after that, I'm not sure. I don't know what my field of interest is at the minute. But that's why this course is good, because it provides the opportunity to try a bit of everything. I recommend having a good relationship with your professors and all the students. It's invaluable and they will definitely help you get through everything that you need. It's definitely challenging, but it's definitely rewarding and very stimulating.
So in the interest of time, I'm going to call a halt there and see if anybody's got any questions. So I'd like to thank you for your attention and encourage you, if you'd like to know more about the course, really anything, anything that occurs to you after this, then please do feel free to get in touch. And the website address is there on the bottom of this slide. I'll leave this up for a moment or two after I stop sharing.
Thank you, Rob. That was fantastic. I loved your presentation, by the way. It's very beautiful thing in and of itself. We've had a lot of, shall I say, patchy ones over in terms of, I felt some of the slides come from a few years ago, but that's obviously really nice. It's great, fantastic. We'll be trying to copy some of those ideas, I think. One of the things I really like, obviously, is quite a modern course, perspective, but actually, funny enough, it reminded me perhaps of reading about science from the early days of science. If you kind of go back, it's almost a bit of a retrograde. Was there any kind of inspiration taken from more kind of 19th century science in terms of looking at this?
That's a very perceptive comment. Actually, it's not 19th century, it's 16th century.
All right, okay, really go back. Okay. Before my time, obviously.
That's a very perceptive comment. So locally, we call this the Hooke course because our kind of poster boy is Robert Hooke. And Robert Hooke is somebody I admire very much. There are actually two strands of inspiration to the course. So one would be that sense that when modern science was first getting shaped by the pioneers, including Hooke. Hooke was actually it's like the first ordinary person to become a kind of famous professional scientist. Everybody before that had been a kind of an aristocrat. And Hooke was a very down-to-earth, practical person. He had a lot of good qualities. He wasn't a perfect man. He had a lot of interesting qualities. In those days, scientists went freely between, astronomy in the morning and chemistry in the afternoon, and instrument building and a spot of maths when necessary, and all this sort of thing. And they hung out in coffee shops and just talked about it with each other. And it was, the excitement of just understanding for the first time using scientific techniques, the way the world works, is something that we're trying to transmit, into this course. And the other inspiration is from two US courses that are running already under the same. So there's a Princeton course, integrated science course, and there's a Harvard course. And we visited those courses and we actually had a look at how they ran. And we've kind of stolen their best ideas in the same, in the same tradition that you're about to follow with the lecture I just given.
With that, I mean, would you like to go further with it? I mean, like you said, would you like to bring in more elements of science? And I suppose if you're looking at America, for example, I mean, obviously they would bring in the liberal arts more broadly. I mean, obviously this can go into other areas of of the humanities and arts as well, I guess. I mean, is that where do you see the expansion? Where do you think you've got the right balance at the moment?
So as I probably as I hope I kind of made clear, this is a relatively small scale thing that we've done, and that was partly, I mean, getting university to approve the course was a bit of a challenge, just because it's so experimental. And so we will develop it, but I think there's an opportunity potentially in the future to do a kind of physics flavored integrated science and a chemistry flavored integrated science and that sort of thing. Exactly how we're going to do that is, we're only just beginning those discussions, so that's not something that's going to be available anytime soon. But I think there is a strong argument for doing it. Absolutely. And it's very interesting that you spotted that as well straight away. Well done.
No, that's good. I'm kind of getting all the bonus points here. On that as well, I was going to ask, just with the students you take on, I mean, I'm just thinking of our own students, and I know that they always have, even where they've got a broad view, they will always have a slight strength or bias, so perhaps they're slightly better at math, slightly better at physics. Do you find that bias is ironed out over the course, or are you finding actually people do end up still in those kind of niches within it?
Well, we only have a year of experience, but I can certainly answer in respect of that first year. And the answer is that people's previous experience allows them to bring something unique that can benefit the other people on the course. That's a positive. So if you've done chemistry and someone else hasn't, it can be a big barrier, it'd be a hurdle, to kind of catch up. And people are doing that, people are catching up. So in terms of the quality of the assessments and things, we don't have an issue. People are catching up quite cheerfully. But I suspect they still retain that intrinsic, in being drawn to a particular area. I don't think that's going to simply go away, because I don't think that just comes from your teaching. I think that comes from deeper inside, So I think you're going to learn. The whole idea is to learn to get confident that you can go and appropriate the principles and the techniques that you need from a different discipline without feeling totally lost, and unable to navigate, but you're still, the whole idea is that you develop as a scientist, and you will have your intrinsic prejudices, in terms of what you want to do. Okay. Your mind is, I mean, I know that, I run a research center as well as doing this, and so, there are people working right down at molecular level and below on problems of how life works, and there are people working at the tissue level and the organismal level, and each one of those people feels that is the right level to work at to solve the question of how life works. So there are personal leanings that continue.
Okay, excellent. I've got a bit of a technical one here, and I'll move on to maybe just careers again after this. I think just with all courses that are perhaps newer or a little bit offset from the others, I think all students always want to know about the application process, because whilst they're applying for your course, they might be applying to slightly different courses elsewhere. So obviously the personal statement in particular, but I take it there's a kind of acceptance that someone might be applying for a very different course at UCL, say, at the same time as applying to you.
Absolutely, yeah. So the typical thing we've seen so far is often people who apply for this course are also applying for natural sciences courses, because that's the traditional way of trying to address this interest in that runs outside a particular discipline. So it's probably worth me clarifying what the difference is. So the natural sciences course, if you go and do natural sciences at one of the older universities, one of the ancient universities, in your first year, you'll be kind of picking from a menu of courses in different departments, and you can blend those things, menu of first year courses in different departments. But from there on, from the end of the first year, you'll just be doing a single subject degree. Occasionally people do dual subject degree or something. But in integrated science, the idea is to try to carry on with this principle of drawing from different disciplines. So we explicitly want you to stay broad rather than focusing into a single discipline. So if you go and do natural sciences at Cambridge, you come out with a degree which is pretty much in chemistry or pretty much in physics or something like that. And here, the idea is you'll come out with an integrated sciences degree, which is effectively evidence that you're able to kind of pop between disciplines if you just want to pick up a new technique. And that's really what we're after. It's very striking. I mean, I mentioned that I'm running a research center. It's very striking the power that comes from drawing techniques from different disciplines when you're trying to address real problems in science. And the reason we're enthusiastic about that is because we do that. We're driven to do that when we're trying to do the best experiment that we can.
Okay, fantastic. I'll move on quickly just over to the career side of things as well. Again, it's quite hard, isn't it? Because you haven't had a graduating class and from that side of things. So I suppose it's more, where do you envisage these students going? I mean, what kind of companies? I know the kind of broadness of the problem solving aspect of it.
So I wrote down some target destinations, as it were, based on people who are coming out of the more conventional School of Life Sciences course in biological sciences, biochemistry, that sort of thing. So let me just share that. And just remember sharing it. So, oops. Yeah, so this information on this slide, this is taken from life, as it were. So these are areas that graduates from the School of Life Sciences end up in. And I put this up really just because the point of this course is to set you up to do a huge variety of different kinds of jobs. So it most certainly is not a vocational course in the sense that it is, training you to do, a particular kind of medicine or something. It's definitely not. What it's doing is it's giving you the mental flexibility and the toolkit to be able to practice science. It's effectively a sort of driving license for science, in all the different areas where scientific knowledge is going to be positive. What I say to people is, if you want to go and be Boris Johnson's science advisor, fantastic, we'll be really pleased. So there's a huge range of possible targets, and that could be, a big biotech company, and that's a typical destination. Some people start their own company. Science business is a very broad category. I mean, you might even be just sort of trading and require some science knowledge to do that well. And that would even qualify, science writing, journalism, publishing, education, of course, and that goes very broad, from teaching the general public about science to kind of, teaching students or whatever. Clearly, this is going to be a, more and more important theme as we go, as we sort of head into an uncertain future globally. I mean, looking after the planet, I mean, this will really help you if you want to do something like that, because you can understand the kind of processes that are going on right from the molecular scale up to the population scale. Computing is a popular destination. There are lots of jobs in computing, and if you know something about big data and how to compute with scientific data sets, that's going to help you tremendously as well. Pharmaceuticals, obvious one. Public health, and that would include global health. If you want to do some work in developing countries improving public health, this would set you up for that. It would set you up to go and do medicine. It would set you up to do scientific administration. I mean, do you see what I mean? It's an extremely general training. It's definitely not specific and vocational.
I was very much thinking, actually, when listening to it, actually, but for any kind of management level position, this is quite a kind of perfect thing, really, because you would naturally have that overview if you were working at a management level in, say, a large pharmaceutical company where you've got lots of different bits of science being done. That was my initial thing. I don't know what you think about that as a possible route for your science business there.
Oh, absolutely. No, I think our aim here is to help you think better, right? And if you're equipped with an understanding of the way the natural world actually works and how to ask questions about how the natural world actually works, effective questions, questions that are informative and tractable, questions that can actually be answered by specific actions, specific investigative actions. That skill is just hugely valuable in pretty much every department of life. I mean, I would say that we lack a good deal of that, for example, in politics at the moment in this country. So, if the world can pick up more scientifically educated individuals going much broader than simply, targeting a science company, but actually thinking more ambitiously about, how can we bring the principles of scientific action and thought into life in a more general way. I mean, you would lose all this, all of the hideous kind of misinformation problems that the world has at the moment, because that level of thinking straight about why do you believe something because of this specific kind of evidence, what kind of evidence is suitable to test a particular assertion about the world, all those kinds of things, you're going to be in much better shape to actually solve real problems successfully.
Absolutely.
There's much more than simply working in science.
That's a brilliant answer. I think a really good place to leave it as well, because that's very much the message we like to get across. This idea of skills and this breadth is something that's really important to us as a school. So thank you very much. And that's been really great, Rob. Really appreciate you coming. Really enjoyed it very much. If you're okay, just to stay on the line just for a few more minutes and we can have a quick chat at the end. Again, thank you everyone for coming and joining us. You've got all the links that Miss Jazz has put in the chat. If you want to go and have a look at more on the Warwick website, find out a bit more about it, you can. If you want to stay on and ask a question in person, you can do that too. If not, we'd like to say thank you very much. And if you could please leave the call now. They've all gone. Thank you.
That was quick.
Great.